That's a lot better. All right. So section 3.7, indeterminate forms and Hopital's rule. So some of you have been using this already. I've seen you guys use this already. It's actually just one of the classes I haven't completely struggled with it, right? That's good. The Hopital's rule, yay. And so some of you have been using this already, and basically it's just if you're working with limits and you get what they call any of these many indeterminate forms, we'll go over each one of them. It's a way of just saying, hi, you can use derivatives in order to figure this out. And so I forgot to change something. I legit forgot to change something here. This is what happens. I'm sorry that these notes are still in my first phase. This should not be so. Thank you. Keep it nice and solid. All right, so let's start with the basics. So here, suppose we have f and g are differentiable, and the derivative is not 0, except possibly at near a, but not at a. Not at. It could be at a, but not near a. Basically, the limit of the derivative isn't 0. So if I have it to be 0, so this is just a book's real fancy way. Basically, if I take a limit and I get right here, 0 over 0, or plus or minus infinity over infinity, right? We call this an indeterminate form. And so we say, well, we don't know what that is, right? And so if we take the limit, we plug stuff in, and it just becomes indeterminate form. What we had to do beforehand was we did like algebra. We like simplified it and did something else and make it simple. But now we're just going to say if it's of indeterminate form, right? And this is an if it's in indeterminate form, then we can say the limit is same to the limit of the derivatives. If it's not in indeterminate form, we cannot say that. And just a real quick example, if I take the limit as x goes to 5, per se, of 5 of x plus 1 over x plus 5, if I take this limit, well, what's the limit here? Well, since nothing, I'm trying to figure out why. It's not, oh, I know why. I don't need, there we go. Let's make it solid. There we go. Round brush. Here, if I take the limit here, I can just plug it in. And so I'll have, this is 6 over 10. But if I took its derivative, right, if I applied the Hopital's rule before then, I would just get 1 over 1, right? If I take the limit as x goes to 5 and I get the limit equals to 1. And notice this is incorrect. And so it has to be, and let me make this very clear, it has to be an indeterminate form before you take the derivative, okay? But if it is an indeterminate form, just go ahead and take the derivative and it works. So just be very careful about that. I've seen one of the biggest mistakes I've seen with the Hopital rule for all my students is that they'll just take the derivative to simplify it, which, 1 over 1 is way simpler than this, right? But if it's not of 0 over 0 or infinity or negative infinity or positive infinity, doesn't matter which signs on it, do not apply it. And so that's just the big warning I want to give to you. So let's actually look at this in practice. So let's actually do a couple of these. Let's look at this. All right, so here, let's apply this. So let's take the limit as this, and so let's just plug it in. So let's just try plugging it in, right? So we're going to try plugging it in. If I just try to plug it in, what do I get? Well, I'll get on top, so the ln of 1 over x minus, or we're plugging it in, 1 minus 1. So this gives me 0 over 0, right? So when I plug it in and I get indeterminate form, which I get here, then I'm allowed to take the derivative. So And so here we're going to say the limit of x approaches 1 of ln of x over x minus 1 is equal to its derivative. Well, let's go ahead and just do d dx of ln. Let me make sure I'm being very clear what I'm doing the first time, and then after that, I'm going to give you a little bit quicker shorthand. I'm going to take the derivative as the top of the bottom. So the derivative of the top, so ln of x becomes 1 over x, and then oops, what did I forget, guys? I forgot the limit. The limit is x goes to 1. That needs to go there. And this also needs the limit as x approaches 1. So here I get 1 over x. And then here on the bottom, I just get 1. Okay, and if I simplify this, this is the same thing as the limit as x approaches 1 of 1 over x, which is equal to, well, if x approaches 1, 1 over 1 is just 1. Okay. And so what what happened here? Let me just be very clear what happened here. We plugged in our number here. We plugged in 1. What we got was 0 of 0. This is one of our indeterminate forms. Once we know that, we can say the limit is equal to the limit of its derivative of the top and the bottom. And then we take the derivative, simplify it, and then here we can just solve this limit by plugging in. All right, so let's do the next one. So let's plug in infinity. Well, let's just plug it in real quick. So we're just going to plug it in. And so when I plug it in, I'm going to get e to the infinity over infinity squared. Well, what does that equal? Well, that's infinity over infinity, right? E to the infinite power is definitely infinity. And infinite squared is still infinity. Technically, what it should be is the limit as x approaches infinity of e to the x equals infinity. Technically, that's the way you should technically do it, is do the top part, do the bottom part, show the equal infinity. Right. Just hit plug in and show this is indeterminate form. Does someone have a comment? So it's derivative plug in again. Yeah, most of the time. So it's plug in is almost always the first step, and then if it is an indeterminate form, take derivative, and then it's solve the limit. 90% of the time, that means plug in, right? So here we're going to do that. So here, this is indeterminate form. Technically, this is what we're doing when we're plugging it in, is we're actually just taking the limit and finding out its infinity. But I just plug it in. So here we can say the limit of x goes to infinity of e to the x over x squared is equal to the derivative. Well, the derivative of e to the x is e to the x. The derivative of x squared is 2x. Well, when I plug this in, notice here, when I plug this in, I still get infinity over infinity. And actually, let me, just for ease, let me write that down here. So this is infinity over infinity. So it's still an indeterminate form. So you know what we do again? We just take another derivative. And so here I get e to the x over 2, right? So I took its derivative once more, since this was also indeterminate form. Now, when I do this, what do I get when I plug it in? I get infinity over 2, so that's just infinity. And does that make sense? And the answer is yes. E to the x grows faster than x squared, right? As you put in values for x. And so that it makes sense that when I take it to infinity, this gets larger faster, that it is going to go to infinity. Okay. All right, let me take a drink as you guys write that down, and we'll go to the next page. You're a little bit muffled, so let me turn you up. Go ahead and ask your question. Oh, so he's asking questions. Woohoo. Hold on, let me go participation.
So for whenever we take the limit, if it's the same exact thing as before, we have to.
I only heard half of that, but I assume that when you take the limit and you get indeterminate, when you plug it in, get indeterminate form, then you take the derivative and you get indeterminate form, yeah, you take the derivative again. You just repeat the process until it's not an indeterminate form.
Okay, thank you.
So if you get infinity, so technically, let me just explain this really quick. So if I have e to the x, that's always just when I take its limit or derivative, it's always just gonna be e to the x, right? But if I had x to like the 70th power, I would have to take 70 derivatives, right? Because in order for this to equal a constant, but eventually it would equal a constant. Um, so um, it works out. There's some things that it just doesn't. If I have e to the x over e to the x plus, sine of x, this one tends, no matter how many derivatives I take of it, I'm always going to get an indeterminate form. And so this one actually will never resolve with the Hopital's rule. But there's other ways to deal with that one. I don't think we get that in depth in this class. All right, so let's look at a couple more of these. So 90% of L'Hopital's rules are going to be something over something, just what it is. All right, so let's do this one. So here, if I plug in infinity, so log of infinity. So as we plug it in, so log of infinity is infinity, right? Infinity, because there is no bound on log, right? It grows quite slowly, but it does go to infinity. This is a cubic root, but this one also goes to infinity. And so remember, what we're really doing is the limit as x goes to infinity of ln of x is equal to infinity, and the limit of x goes to infinity of the cubic root of x is equal to infinity. So that's technically what we're doing. I'm just skipping that part and just saying, because, if you just say plug it in, I get infinity, you don't need to write all this. So we're going to take its derivative. So let's go ahead and do that. So we have the limit as x approaches infinity is of ln of x. Oops. Hi, my computer got super crunchy for who knows why. Why are you being so crunchy, computer? Apple's supposed to have an event. Maybe they'll buy a new computer after they announce a new one. All right, so we have this. So we take the derivative. So the derivative of ln of x. You are being really crunchy. I know how to at least export this as a PNG real quick. Hi. Yep. Hey. Bye. I don't know why you're being so crunchy. Yeah, don't say. Hopefully that'll make it slightly less crunchy. Yeah, there it goes. All right, so I have 1 over x, and then here, if I take this derivative, so remember this is the same, so x to the third is the same as 1/3 x, and so I get 1/3 x, and then 1/3 minus 1 would be minus 2/3. All right, so if I put this together, so here here I need to do some algebra before I plug stuff back in. So this is, so I bring this x to the bottom, and so I'll have 1 over 1/3, and then I'll have x to the minus 2/3 times x, which is the same thing as x to the 1. This 1/3 I can write up top. Oops, I'm forgetting my limits. Imagine this is written here and here. In fact, I'll write it here like a good person. And so this 3 goes up top, and then this becomes just the cubic. And so this just becomes x to the third. So negative 2/3 plus 1 is a third. If I take this limit, I get this goes to infinity. and this stays 3. So remember, so if I just plug this in, I get, I'll get 0. Since this is some number, remember, anything over infinity is 0. Okay, so we get just a 0 here. All right. Let's do this next one. You guys asked to make sure we did. I don't always do the trick ones, but you guys wanted me to do that, so I'll make sure to do that. So let's look at this. All right, so if we plug in 0, so tangent of 0 is 0, right? So 0 minus 0 is 0, and then 0 cubed is 0. So this is 0 over 0. So this is of indeterminate form. You do, when you're doing the exam, please make sure you announce somewhere or show somewhere that you have an indeterminate form, right? This is 0 over 0. So we can go ahead and take the derivative. So we'll take, so this, oops, not tax. If you haven't done your taxes, go ahead and do so. Take the derivative. So derivative of tangent is secant squared x minus 1 all over 3x hold on. Oh, okay. Just making sure the question got answered. Okay, so what do we have here? So we have secant squared x over this. So what's secant squared? So what do we have here? Well, what's secant of 1 or of 0? Sorry, secant is 1 over cosine, right? 1 over cosine. Well, cosine of 0 is 1, so 1 over 1 would be 0. So this is 1 minus 1, which is 0. Right. So this is indeterminate form again, right? Because up here, if I plug in 0. Oh goodness gracious! I keep forgetting the right one. So this is 0 over 0. So this is indeterminate form again. So we're going to have to take another derivative. So we have the limit. So secant squared. So if I have something squared, it would be 2 secant x plus the derivative of secant. Well, derivative of secant is secant tangent x. Okay. So here we're using chain rule, and then derivative of the 1 is nothing. And then here we'll have over 6x. Well, if I plug this in, what do I get? What do I get here? Oops, I forgot I wrote the limit, but I need my thing a little long. Anyone know what we get here? Well, I get 0 on the bottom again, and I'll have 1 times 1 times 0, so I get do this again. So what must I do? Give up? Yes. Give up is what we should do, right? And so here we get 0, 0. So we just take it one more time, right? We just do it one more time. And so we should get a, let's see, hold on. I'm gonna see something real quick. Is there a better way to do something here? So here we get limit as x approaches 0. So here I'm going to have a third. I'll go ahead and simplify that. I'll just pull out all the constants. We're going to have nothing on the bottom, and then we're going to have secant. So the derivative of secant squared times tangent. That just turns into a little bit of a mess. I'm not gonna lie to you guys. There's a way to simplify this. I'm trying to think if I can simplify this without having to do too much craziness for you guys. No, I don't think so. So we'll just go ahead and do it. So this will become, you know what? Let's just, I am secant squared x. I think I need to type this in very carefully here. Let me just remind you how to do it in Wolfram Alpha. I mean, we could do it with product rule and just take a couple seconds. Let me just remind you how to do it in Wolfram Alpha. That way, when you get to this point, you have a way of checking it. All right, so we can take this derivative. And so this is what we get, right? We get secant. So this derivative gives me secant to the fourth plus 2 tangent squared plus secant squared, right? So this big piece, right? And so we're going to get secant to the fourth, secant x to the fourth, plus 2 secant x squared plus tangent squared. All right, now if I plug in 0, tangent x of 0 is 0. So this whole term turns into 0. This term just turns into 1. So at the end of the day, this equals a third. Okay. Now, could we have done that, the other way? Yeah, because if I'd done it the other way, I'll just show you. So if this is secant squared, if I hold this constant and take the derivative tangent, I get secant squared times secant squared. So that's secant to the fourth. If I hold this, if I hold tangent constant and I take the derivative of secant squared, I get 2 secant squared tangent squared. And or tangent times the tangent, and that gives us this. And so we could have done it by hand. I just wanted to show you how to do it at once, because every now and then you guys get uncomfortable taking derivatives, and it's just nice to know how to check it. Okay. All right, so this one's a little bit of a mess, but you just kind of work through it. So here we get indeterminate form, work it, indeterminate form, and then eventually it clears out. And so usually if you see something like x to the third or something, if you just take enough derivatives, it'll clear out and become clean. So let's do this one. So here we have this. I'm going to take x, and it's going to go to pi negative. So I'm going to go to pi, but on the I'm going to go to pi, but I'm going to do it from the left-hand side, right? We're coming in from lower values than pi. And the reason that's important, because this sine of pi is 0, right? Cosine is 1 minus 1, so this is 0 over, so this is equal to 0 over 0. If I came in from the positive sine of pi, this will be, I don't know if that matters, hold on. Pi, hold on. Am I being silly? What's cosine of pi? It's not 1. Here I get 0 over 1 minus 1. But this is minus 1, right? What's cosine of pi? Cosine of pi is minus 1. Be very careful here. And so is this an indeterminate form? Is 0 over 2 indeterminate? No. Right? And so here, but we have our answer though. We found out what the answer is. It's 0, right? The limit of this is 0. And so we just have to be careful, right? Because I was like, oh, this is Hopital's rule. I want 0 over 0. So I just making up false math to make it 0 over 0, because cosine of pi is not 1, it's a negative 1. And so 1 minus a negative 1 is 2. Now let's pretend I made the mistake for 2 seconds. And you'll get a different answer, right? Because if I took this derivative, I'll get cosine up top, I'll get sine on the bottom, and if I take that as the limit as x goes to pi, on the negative side, what do I get here? I'll get cosine. This will give me minus 1 over 0, which is infinity, which is wrong, right? So this is super wrong. It's 0, not negative infinity. So please, 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 please. So I'm going to write, please check if in the indeterminate form. Okay, so that means do not do it if you're not supposed to. So please check if it's an indeterminate form. If it's not, just go ahead and just solve it regularly. All right. Oops, that put the dot in the wrong spot. It should be 0 dot infinity, not dot 0 infinity dot. Sorry about that. So here we have an indeterminate form of product. So let's pretend I have, if I multiply two functions and I get 0 times infinity. We call that the indeterminate form for a product. So we can deal with it one way. Basically, you just write you just write it as a quotient and then just write 1 over 1 or 1 over g or 1 over f on the bottom. And let me show you how that's done. Let me just show you how that's done directly. All right, so here, so I take the limit as x goes to 0 positive, and 0 positive is important in this case. And so x goes to, so if I plug it in, I get 0 here, and then I'm going to be times, well, the limit as ln of x goes to 0 positive, remember where ln of x looks like this, right? So this is going to be negative infinity. And so this is indeterminate form of this type. So this is okay. So I have 0 times negative infinity. I forgot my negatives. I'm going to make that my handwriting a little bit better. Negative infinity. This is an indeterminate form. So what am I going to do? I am going to write 1. So I'm just going to write. So I'm going to write the limit as x goes to 0 positive is the same as x ln x is the same thing as the limit as I go to x to 0 positive of ln x over 1 over x. And so I'm just going to write this as 1 over x. This is algebraically the same as that. What does this go to? Well, this goes to infinity. This goes to infinity, or this goes to, hold on. This goes to negative infinity. This goes to positive infinity. So I have infinity over infinity, right? So this is infinity over infinity. So this is an indeterminate form of where we can apply the Hopital's rule. And so we just take its derivative. So here, the derivative hi, computer, why are you crunching? And then here, this is x to the minus 1. So this becomes minus, so this is also, remember 1 over x is equal to x to the minus 1 power. So I bring down the minus 1, and then be x to the minus 2 power. And then if I simplify this, limit as x goes to 0 positive would be 1 over negative x to the minus 3 power. Oh, no, wrong way. Wrong way. This is just 1 over x to the minus 1 power, because here I get a positive x if I move this down below. Yes. but this is the same as, actually, hold on. I'm making this harder than it needs to be. Let's move this up. So this becomes -1, but if we move it back up, it's just -x. Once you do all the algebra, you get to this. And then you can just plug it in, and what do we get? We have 0. So we know which one it is. Because usually if you see indeterminate product 0 times infinity, one of them, it's either probably going to be 0 or infinity once you work out the math. Okay. All right, so I'll leave this up for you guys to write. I will export it since my computer's being super crunchy. I don't know why it's being so crunchy today. I just restarted it. All right, let's get rid of this. Don't see. I just exported it. All right, so let's just do 2 more. All right, so your book goes into a couple more. So here I have indeterminate differences. So here if I have a form of infinity minus infinity of 2 functions, you can deal with this by converting the difference into a quotient. For instance, you can use common denominators for rationalization. There's 1,000 ways of trying to do it. Your book's just being cute to say each way. As long as you can write something as something over something, you can use the Hopital's rule. So if you can make something into a quotient, you can use the Hopital's rule. The only one that's kind of unique is the powers, but we'll get into that in a second. So let's have this. If I plug this in, and I'm going to take this to pi over 2 to the negative side, so that means coming in from the left. This goes to infinity, this goes to infinity, and so this is infinity minus infinity. And so here we have our indeterminate form. So what do? Well, we just kind of rewrite this for a little bit. So we just do, see if we can write this somehow as a quotient. And so here, secant is 1 over cosine of x, and tangent is sine over cosine of x. So here I'm just rewriting this, and then I can rewrite this as 1 minus sine of x over cosine of x. Oops, I forgot my limit. Equal sign. All right, so here I've now written it as a product. No, not a product, a quotient. And here if I plug in pi over 2, I'll get 0 and 1 minus 0. So this is 0 over 0. So here I can apply L'Hopital's rule and then take its derivative. And so I'll have limit as x approaches pi over 2 from the minus side. The derivative of 1 minus sine is just minus cosine of x. The derivative of cosine of x is minus sine of x. The minus signs cancel, so I have sine over cosine. And so here if I plug in this, I'll have 0 up top, 1 on the bottom, and so I have 1, and so I have 0 over 1, which of course is just 0. Okay. Can you go back to example 4? Sure, I will when I'm uploading the next set of, when I'm opening up the next set of notes for you guys. Okay, I'll post that as we do that. And so what do we do here? So here we had a difference of infinity minus infinity, and this is how it looks. So we can say, all right, can I somehow get a common denominator between these two? And we did, right? Because they both have cosine. There are different ways of doing this. And we get it into what we want is the indeterminate form of 0 over 0 or infinity. That's what really the whole goal of this is. If you have one of these many indeterminate forms, try to make it as a quotient that is 0 over 0 or infinity, and then take the derivative. If you put it into a quotient and it doesn't equal one of those, well, that means there is a different method to solve it than the Hopital's All right, so, and then here we have power. So if I have 0 to the 0 power or infinity to the 0 power, I've like, oh, I don't know, I don't really know how to deal with this. And then we'll have like 1, 2 plus or minus infinity. So all these types give us indeterminate forms, right? Well, 0 to the 0 power, well, anything to the 0 power is supposed to be 1, but 0 to any power is supposed to be that. And so it's like, well, what is that supposed to be? And so you'll have to deal with that. And then here we'll have infinity to the 0 power, so we have infinite, but anything to the 0 power should be 1. Well, which one wins? And then here, if I have 1, but if it's not exactly 1, if I raise it to the positive or negative infinity power, it's going to become either 0 or infinity. So this since the limit is it approaches but does not reach, these all forms become indeterminate. Okay. And so there's a couple ways of doing it. The first one is if you just let, if you let, so here if I have one function, like this one goes to 0 and this one goes to 0, so we have this form. We can do ln of y and we'll write it like this, and then we can start messing with it. Or here we can write it as e to this, and we can start messing with this. And I'll show you how this works. This doesn't make too much sense by looking at this. You're like, okay, what's this? Well, let me show you in practice. All right, so here, if I plug in this, what do I get? I get 0 raised to the 0 power. This is one of my indeterminate forms. Okay, so I'm going to rewrite this. So I'm going to rewrite this using this method. So I'm going to say the limit as x approaches 0 plus of x comma x is the same thing as the limit as x approaches 0 plus of e x ln x. And so here I'm pulling, so here I'm taking my power, I guess taking my power, putting it out front, and then writing ln of what's here. I guess if I chose something besides x and x, it would be a little bit more clear what's going on. Well, do I know how to deal with this? And the answer is sure, right? I just need to figure out what's up here. And so what's the limit of x reach going to 0 plus of 0 ln of x? And this is the reason I kind of chose this one, of x ln of x. So we're just looking, so I'm going to take this and figure out what that limit is. So we're going to deal with this in isolation for a second. So this is not equal. I'll make that very clear. This is not equal, but I'm going to take this part and I'm going to try to figure out what that is. Well, have we done this? Did we do this? Of course. I want it. This is why I save it. This is exactly why I save it. Hi, can I have what I just literally popped out 2 seconds ago? Whoop. Yeah, we just did this one, right? We just did this one. It was example 6. Whoop. Yeah, we know what this ends up being. This ends up being 0, right? Now, granted, do we have to do a lot of fanciness to get there? Yeah, we did, but it ends up being 0, and so we already know what the solution is, right? So this ends up being 0. So what does the limit end up being? Well, here, I know this limit ends up coming to be 0, so this is equal to the limit of x goes to 0 plus of e to the 0, because I just know how this one works out. And so this is equal to 1. Okay. And so what you do here is you switch this to this. These are equivalent. These are actually equivalent statements from what we learned from doing, if I take a log of if I take e to the x, because basically I just raised it to the power of e and then took its log of x to the x. That's basically what you did. So I'm just applying a function and its inverse to get back what I wanted. But by doing so, I get this into a form I can determine what it is, and then I just raise e to that power. That's all you're really kind of doing here. So